Just what is mathematics? Is it substantially different from other subjects? Is it just a game, or are mathematicians discovering something real about the structure of reality? Welcome to TOKCAST on the nature of mathematics. The rules of chess are pretty straightforward once you learn them. The bishop. Yes, the bishop can go as far as you want, but it's restricted to moving diagonally. The rook can also travel from one end of the board to the other, but only down columns or along rows. The king, any direction at all, but it can only move one square at a time. Okay, unless it's castling. These few simple rules lead nonetheless to a rich array of possible games. In fact, the number of possible games, despite being unimaginably large, is in fact finite. One estimate is that it's around 10 to the power of 10 to the power of 50. That aside, the rules of chess seem to be arbitrary. They could have been different. We can imagine that the bishop might have been limited to moving only 2 squares, rather than the length of the board. Or we could imagine a game where the queen simply doesn't exist. Or that another piece takes the place of half the pawns. The possibilities seem endless. And the game of chess we do have is simply the result of convention and tradition. Is mathematics like this? Is it just a self-consistent set of rules that permit games to be played? Could we change the rules and so play a different game? This idea is a relativist one. It is a popular idea, and it permeates much of academia, especially among some in the humanities. This is not to say that all and only those in the humanities think this way. Certainly, some mathematicians believe they are simply playing games. Famously, David Hilbert, the great German mathematician, who worked on the very foundations of proof theory, probably thought something like a version of this idea. But he's notable as being an exception in this regard among mathematicians. And anyway, funny as it may seem, a mathematician is, in fact, not necessarily the best person to consult about the nature of mathematics. As we will come to see more and more in the Theory of Knowledge course, while we should never rely solely on any authority, a philosopher, in this respect, is likely to have a more informed and considered opinion. In particular, in this case, a philosopher of mathematics is. This is kind of similar to the way that a pilot of a 747 might be a highly competent user of an aircraft and yet not have a very complete knowledge about how precisely the wings and engines come together to allow him to do his job. Sure, he might have a very good idea, but really it's not essential to his day-to-day business to know that much about aeronautical engineering. An aeronautical engineer, on the other hand, you get the distinction. Philosophers of mathematics in general do seem to be realist about the nature of mathematics. Mathematicians themselves are also generally realist about their own subject. Realism means that there is a reality out there independent of the human mind. Mathematical realism, therefore, is the idea that mathematical entities are also independent of the human mind. This means mathematics is discovered, not invented. Relativist philosophers, on the other hand, generally all have this in common. Truth is a matter of perspective. This is equivalent to the statement, there are no absolute truths. This may cause one to wonder about the truth of relativism then. Is relativism true? If it's true, then there is at least one truth that is not a mere matter of perspective, namely, relativism. But then, why should relativism be privileged except on dogmatic grounds? I'll have more to say about relativism and the related theory of postmodernism in a future TOKCAST. As all such relativist ideas on the nature of reality can be similarly seen to collapse when the foundational self-contradiction that props them up begins to crumble, so too can the relativist view of mathematics be criticised. mathematical truth is not a mere matter of taste. Unlike chess, the rules cannot be so easily changed. Imagine you wished to change the theorem that 1 plus 1 equals 2 to become 1 plus 1 equals 3. Can you? Is it merely by convention we say one of these is true and one is not? Well, imagine we did suddenly decide that 1 plus 1 equals 3. Then what? Well, the word 3 and the symbol for it would come to mean what we mean now by 2. Then what happens to the abstract entity to which 3 previously referred? Well then, we would need a new word and a new symbol. Perhaps we could use 2. Perhaps we could use Graham. Whatever we did decide to use, the entire edifice of the remainder of our mathematics would change, and it would change in order to consistently accommodate these changes. And, in the end, we would have changed nothing but the symbols. It is worthwhile pointing out here that mathematics works. Mathematics is not merely an invention of the human mind, like say the great trilogy, Lord of the Rings, because mathematics enables us to make predictions and discover new things. If mathematics were a mere invention, then we should not expect it to be so accurate in the predictions it enables us to make. No work of fiction is able to predict, with anything approaching the same level of fidelity, the things that mathematics, in partnership with science, can. The laws of physics are expressed mathematically, and the fact that they are mathematical in form is not only somewhat mysterious, but also fortuitous. Imagine that we wish to calculate exactly how long it will take for a rock dropped from a cliff to splash into the ocean below. Physics tells us that if we know just a few things, like the height of the cliff and the force of air resistance, then we can write down a mathematical formula, perform a calculation, and make a prediction with an extremely high degree of accuracy. If mathematics were simply all made up, and was just a game, why should we expect it to work in this way? It seems that mathematics is not something we can make up any more than any other part of reality. Mathematics is there to be discovered, and we can be truly right or wrong about it. When we look at something purely mathematical, like say the distribution of prime numbers, we find something quite surprising. The prime numbers are distributed in a way we do not completely understand. We cannot predict exactly when, among all the natural numbers, the next prime number will pop up. The highest prime number found, as at the end of 2009, has around 13 million digits. What the next one will be, no one yet knows. But we do know it's out there. Euclid, in 300 BC, was able to prove that there are infinitely many primes. So the next highest prime number exists. We just haven't found it yet. But in what sense does it exist? Well, it does not yet exist in any physical way, and so this is why we say mathematics is about abstract entities. As far as prime numbers go, however, it has even been suggested that communication with alien intelligence could, in part, be recognised by an embedding of prime numbers in a radio signal. In other words, we should expect aliens, who would speak none of our terrestrial languages, would nonetheless know the same basic mathematics, especially if they are capable of using electromagnetic radiation for communication purposes. It turns out it would not matter if the number system they used was base 10 like ours, base 60 like the Babylonians, or base 2 like a computer, or any other base. The prime numbers are somehow out there to be discovered, and you can express the same number using any system you like. The prime number that in base 10 we know as 7 is 0, 1, 1, 1 in binary. Prime numbers are not an invention. They are a series of numbers, some of which have been discovered, and an infinity more out there waiting to be discovered. Again, we come back to the point that mathematics in general is something that is discovered, not invented. There are many flavours of realism, which is the alternative to the relativist position on mathematics. It is worth looking into, for example, Platonism, logicism, and formalism in more detail. But the type of realism I will discuss is a type of what is called empiricism. But for the sake of clarity, I'm simply going to call it the realist perspective. The idea is this: mathematics is about necessary truth. Mathematics is a language, yes, and a tool, certainly. But in the end, pure mathematics is the study of necessary truth. It is important to distinguish between what are known in philosophy as contingent truths and necessary truths. And that's what I'll do next. So what's all this about necessary truth? Well, a necessary truth is one that could not have been otherwise. It is true by virtue of the meanings of the terms that make it up. For example, a triangle has 3 sides is a necessary truth. The meanings of the words triangle, 3, and sides in this sentence mutually define each other. I do not even need to draw the triangle for you to know the statement is true. If I drew something that was 4-sided and called it a triangle, I would be wrong. This reminds me of a joke a philosophy lecturer of mine once told me. If you call a horse's tail a leg, how many legs would it have? Well, how many legs? It would have 4. You can call the tail whatever you want. A horse has 4 legs. Necessary truths are like this. It is simply not possible for them to be otherwise, without contradiction. All bachelors are unmarried men. If you are in Sydney, then you are not in Melbourne. Mathematical truth is like this, therefore. Mathematical truths are necessary truths. It is necessarily the case that 1 + 1 = 2. It cannot be otherwise, so you can't simply change the rules. We can actually rigorously prove, for example, that the theorem 1 + 1 = 2. It actually takes around half a page using something called Peano's axioms of arithmetic, the underlying rules of basic arithmetic. These are things like that for any number x, then x + 0 = x. And for any number x, if you add 1, then you get the immediate successor of x, and so on. I'll be coming back to what axiomatic systems are all about in the next TOKCAST. So that's what necessary truth is. Truths that cannot possibly be otherwise, and so which entail a contradiction if you deny them. What about that other sort of truth I mentioned? I called it contingent truth. Contingent truth is the truth of all natural and human sciences. It is truth that could have been otherwise. For example, the true statement, the Earth is the 3rd planet from the Sun, is a contingent truth. You can certainly imagine a possible world where Venus did not exist, making Earth the 2nd planet from the Sun. Or what about World War II ended in 1945? Again, a contingent truth. You might be wrong, but there is no contradiction in saying World War II ended in 1994. There is nothing about the definitions of World War II and ended in 1994 that entail a strict logical contradiction. There might be some empirical facts that lead to the statement being false, but it is false based upon knowledge of the physical world. If one never knew anything else about World War II, other than it began in 1939 and ended in 1994, one might go through life with this falsehood. On the other hand, one cannot consistently believe in 4-sided triangles. So there is a distinction to be made here between what is a necessary truth and what is a contingent truth. This distinction, it turns out, is also important in considerations about the existence or otherwise of free will. Leibniz, one of the inventors of calculus, along with Newton, was one of the greatest philosophers of all time, and was able to solve the problem of free will in a universe with an omniscient God, that is, a God who knows everything, including all of your future actions. Whether you believe in an omniscient God, or whether you believe that the laws of physics ultimately determine all of your future actions, Leibniz is able to reconcile these views with free will. And that is something I'll talk about in a future TOKCAST. Now, just because mathematics is about necessary truth, does this make it certain? It turns out we cannot be certain about mathematical truths. This is because in order to establish something as mathematical fact, we need to prove it. Now, a mathematical proof, or a purely logical proof, is a process. It is a process that usually a person goes through using pen and paper, or a calculator, or their mind. I say usually because some proofs today are completed entirely by computers. Whatever the case, a proof is a process. In fact, it is a physical process. Whether the theorem one is interested in is written in symbols on paper, or it is simply conceived of in the mind, or it appears on a computer screen, or it is calculated using a machine, the process of proof relies upon some physical system. Now, machines can malfunction, mistakes can be made on paper, and brains can make errors. All of this adds up to say that mathematical theorems can only ever be as certain as the proofs used to establish them. And because a proof is necessarily a physical process, it is going to be subject to the same fallibility as our knowledge about any physical process. In short, proofs are not abstractions, they are computations. And a computation always requires a computer. And it does not matter if that computer is made of silicon or biological neurons. This point of view is not shared by all mathematicians and philosophers. It is worth looking at alternative points of view, including Platonism. Platonism is the idea that mathematical entities exist in another abstract realm that we do not have complete access to. Importantly, the proof process on this Platonic view is generally also regarded as an abstract process that can be separated from the physical world, and therefore we can get mathematical certainty by somehow tapping into the non-material abstract world of Platonic forms using our non-material minds. Some other philosophers think this view is misguided, and the confusion stems in part from confusing the processes of mathematics with its subject matter. Mathematics is about necessary truth. The truths that mathematics studies are themselves certain, but this does not mean our knowledge about these truths is certain. As David Deutsch so succinctly puts it, necessary truth is merely the subject matter of mathematics, not the reward we get for doing it. The objective of mathematics is, therefore, not mathematical certainty or even mathematical truth. Rather, it is mathematical explanation. Even in proofs which do not involve diagrams, we must still use symbols or calculators or our brains. All of these things are physical objects, and so the argument still holds. That is, our knowledge of mathematics is based upon our physical theories about how physical objects behave. For this reason, we can be no more certain about the truths of mathematics than we can about how we think physical objects behave. Ultimately, our confidence about how physical objects behave is based upon our scientific theories about how those physical objects behave. Understanding the relationship between those physical objects and the mathematical proof we are undertaking with them, be that pen and paper, a computer, or a brain, tells us how confident we are entitled to be about our deductive proofs. It is sometimes assumed, at least tacitly, that there is a hierarchy of argument in academic discourse. There are mathematical proofs that are absolutely certain. There are scientific arguments that, while not absolutely certain, are certainly still very reliable. And finally, there are philosophical arguments, and they're a mere matter of taste. Here, I have used a philosophical argument to establish that mathematical explanations rely upon our scientific theories for their veracity. It is simply not true that mathematics gets us certain truth. It's useful, it can be beautiful and elegant, and it is essential in science, but it is not certain. Really, all claims about the nature of reality and truth are philosophical. Philosophical arguments should be logical and so consistent and based on as few assumptions as possible. In the end, it is a good philosophical argument that gets us to our understanding of mathematics as a subject about necessary theorems whose truths are established by the physical process known as proof. But are there limits to the proof process? Or could we one day program a computer who'll be able to prove all of those necessary true theorems of mathematics? Well, that's the subject of the next TOKCAST.
For resources and links associated with TOKCAST, visit the TOKCAST website at www.tokcast.net.